Pictured here is a Smith chart. It gets its name from its inventor, Will Smith, while he was working at Bel Air Laboratory. Wait, that can't be correct. Wait, Will Smith? Fresh Prince? Hold on. Let me ask the producer. Hey, Jim, is it Will Smith? No? Philip. All right. No, definitely not Will Smith. The inventor was indeed Philip Smith of Bell Laboratories. Anyway, the Smith chart is just a graphical tool used to match transmission line impedances in electrical circuits. Wow, that was a lot of information. Match what? What kind of circuits? Let's just break it down. Here's a circuit diagram with a load on the right and a source on the left. The source is able to send a signal to the load via transmission lines. Notice that the load has an impedance, ZL. The transmission line impedance, Z0, is often called the characteristic impedance. One interesting thing about this circuit is that electrical signals being sent from the source to the load can be reflected backward. This is the case when the load impedance, ZL, does not match the impedance of the transmission lines, Z0. One way I like to visualize this effect is to imagine a big blue wall at the end of the transmission lines just before the signal gets to the load. When ZL and Z0 don't match, the wall appears and bounces signal back to the source. Not a good thing. But if somehow we could get Z0 and ZL to match, the wall would disappear and our entire signal would go from the source to the load without any trouble. Sticking with this blue wall analogy, sometimes the blue wall is not completely solid. This occurs when Z0 and ZL only partially match, at least enough to let some of the signal through. The rest of the signal gets reflected back at the source. The ratio of signal reflected back compared to how much is transmitted to the load is called the voltage reflection coefficient. It is denoted by the Greek letter gamma. So you're probably wondering how to find Z0, ZL, and the reflection coefficient on the Smith chart. In due time, my young grasshopper. But first, let's get a little more familiar with the Smith chart. As you can see here, the Smith chart is round in shape and can be used to summon demons from the abyss. Oh wait. Jim! Wrong graphic! And we're back. Our producer Jim has been laid off and I found the Smith chart. The Smith chart is round in shape and is composed of circles of constant resistance, seen here in red, and arcs of constant reactance, seen here in blue. When put together, you are able to plot impedances on the Smith chart. Let's try it out. Using our circuit from before, we have the characteristic impedance Z0 and the load impedance ZL. In order to plot ZL on the Smith chart, we must first normalize it. This is done by dividing ZL by Z0, resulting in a normalized load impedance. For example, if we have a load impedance of 40 plus 30J and a characteristic impedance of 50 ohms, we can use the normalization equation to get 0.8 plus 0.6J. We can plot this on the Smith chart by first looking for the real part, 0.8, along the center horizontal line. Next, we can look for 0.6J. This will lie on an arc above the center line because it is positive 0.6J. If it were negative 0.6J, we would have to look below the center line. The normalized load impedance, seen in green, is where the 0.8 circle and the 0.6J arc meet. Now that we've plotted the normalized load impedance, we can find the voltage reflection coefficient. Let's zoom out and take a look at the bottom of the Smith chart. Here we can find a measurement scale that can be used to measure the voltage reflection coefficient. First, we measure the distance from the center of the circle to our plotted point, then translate it onto the ruler. It looks like our voltage reflection coefficient is about 0.34 toward the source. So there you have it. Plotting impedances and finding the voltage reflection coefficient is only a small taste of what the Smith chart can do. Hope this video has helped you to understand some of the basics. Stay fresh!